December 1917. The cold waters off the British coast. A German U-boat glides silently beneath the waves, its commander scanning the surface through his periscope. Above, a British merchant convoy churns toward port, laden with grain, coal, and ammunition. The destroyer escort sweeps the area with the Royal Navy's latest submarine detection equipment. The hydrophone operator presses his headset tight against his ears, listening. Nothing. Just the roar of their own engines, the crash of waves, the grinding of propellers. The U-boat fires. 2 torpedoes streak toward their targets. By the time anyone realizes what's happening, 2 merchant ships are sinking, taking their precious cargo and dozens of men to the bottom. The destroyer races to the last known position, drops depth, charges blindly into the murky coastal shallows. The explosions send geysers of white water skyward. But when the foam settles, the U-boat is gone, vanished into the acoustic chaos of shallow water where rocks, tides, and thermal layers make detection nearly impossible. This scene repeated itself dozens of times that winter. Britain's submarine detection technology, which had shown promise in deeper Atlantic waters, was failing catastrophically in the shallow coastal zones where U-boats now hunted with impunity. The German Imperial Navy had adapted their tactics, and Britain was paying the price in blood and cargo. The island nation that ruled the waves was being slowly strangled by an enemy it couldn't see or hear. What happened next would change naval warfare forever. In a desperate gamble, the Admiralty would assemble an unlikely team of civilian scientists and military specialists in Portsmouth. Working with salvaged wreckage and improvised equipment, racing against time as merchant ships continued to sink, these determined engineers would create technology that could finally hear death approaching beneath the waves. This is the story of how Britain's acoustic warfare pioneers turned the tide against the U-boat menace in home waters, saving the nation from starvation and defeat. The crisis had been building for months. By late 1917, German U-boats had sunk over 3 million tons of Allied shipping that year alone. The unrestricted submarine warfare campaign, resumed in February, was designed to force Britain to its knees before American forces could arrive in strength. And it was working. Food reserves in Britain had fallen to just 6 weeks' supply. Rationing was introduced. Queues formed outside shops before dawn. The government quietly drew up plans for surrender negotiations should the situation deteriorate further. The convoy system, introduced that spring, had helped protect Atlantic crossings. Merchant ships traveling in groups, escorted by destroyers and armed trawlers, proved harder targets than lone vessels. Losses in mid-ocean declined. But the U-boats simply shifted their hunting grounds. The shallow coastal waters around the British Isles, the Irish Sea, the English Channel, the approaches to major ports, these became killing zones. Here, in waters less than 200 feet deep, German submarines could lurk near the seabed, hidden in the acoustic clutter. They would wait for convoys to pass overhead, then strike from below before slipping away into the murky depths. British hydrophone technology, the underwater listening devices that were supposed to detect submarines, simply couldn't cope. The equipment had been developed for deeper waters where sound propagated more predictably. In shallow coastal zones, everything changed. Sound waves bounced off the bottom, refracted through layers of different temperature and salinity, scattered off rocks and wrecks. The hydrophones picked up a cacophony of noise. Waves breaking on distant shores, tidal currents rushing through channels, the propellers of friendly ships, schools of fish, even shrimp, countless millions of them, crackling and popping as they snapped their claws. Finding a submarine in this acoustic chaos was like trying to hear a whisper in a thunderstorm. Lieutenant Commander Charles Ryan stood in the Admiralty building in London, presenting the grim statistics to a room full of senior officers. Ryan was one of the Navy's few acoustics specialists, a former physics lecturer at Cambridge who had joined up in 1914. He had spent the past year studying why hydrophone detection was failing in coastal waters. His report made for uncomfortable reading. In November alone, U-boats operating in home waters had sunk 23 merchant ships, 4 fishing trawlers, and 2 Royal Navy patrol vessels. The hydrophone-equipped escorts had detected the attacking submarines in exactly 0 instances. Not a single contact, not one successful interception. The technology, Ryan explained, was fundamentally inadequate for the environment. The hydrophones were non-directional. They could tell an operator that a submarine was somewhere nearby, but not where. In the open ocean, with relatively few other vessels around, this was manageable. Escorts could search systematically. But in busy coastal waters, with dozens of ships passing daily, the hydrophones were overwhelmed. They couldn't distinguish between the propeller noise of a surfaced U-boat 5 miles away and a fishing boat half a mile in the opposite direction. An admiral interrupted. What about the directional hydrophones the French had developed? Ryan shook his head. The French systems used large, fixed installations on the seabed, connected by cables to shore stations. They worked well for protecting specific harbor approaches, but they couldn't protect the hundreds of miles of coastline where U-boats operated. Britain needed mobile systems that could be mounted on patrol vessels. Systems that could not only detect submarines but locate them precisely enough to attack. The room fell silent. Then a captain spoke up. What would it take to develop such a system? How long? Ryan hesitated. The physics was complex. The engineering challenge is immense. 6 months, perhaps, maybe a year. Another officer slammed his hand on the table. They didn't have a year. They had weeks, maybe days, before the shipping losses became unsustainable. Ryan was given his orders. Assemble a team, get access to whatever resources he needed, and solve the problem. Fast. Ryan arrived in Portsmouth 3 days later in mid-December 1917. The naval base was a hive of activity. Destroyers and patrol boats coming and going. Merchant ships being fitted with defensive guns. Dockyards working around the clock. He had been assigned a workshop in one of the older buildings near the harbor, a drafty Victorian structure that smelled of oil and salt. His team began to assemble. The Admiralty had sent word to universities, research laboratories, and technical colleges across the country. They needed experts in acoustics, electrical engineering, materials science. Anyone who might contribute to solving the hydrophone problem. Within a week, an eclectic group had gathered in Portsmouth. There was Professor Arthur Bennett, a physicist from Manchester who had studied sound propagation in water. Dr. Margaret Hartley, one of Britain's few female electrical engineers, who had been working on radio detection equipment. Commander James Thornton, a submariner who had served on British boats and understood how they operated. A dozen junior engineers and technicians, some from the Navy, others from civilian firms, and Ryan himself coordinating the effort. They began by examining the existing hydrophone equipment. The standard British system consisted of a single microphone lowered over the side of a ship on a cable. The microphone picked up sound from all directions, feeding it to an operator wearing headphones. The operator would listen, trying to distinguish submarine propeller noise from the background cacophony. It was, Bennett observed dryly, like trying to find a specific instrument in an orchestra while standing in the middle of the percussion section. They needed directionality, the ability to determine not just that a submarine was present, but where it was. The French had achieved this by spacing multiple hydrophones far apart, comparing the time it took for sound to reach each one. The difference in arrival times revealed the direction of the source, but the French installations were huge, permanent structures. Ryan's team needed something that could fit on a patrol boat. The breakthrough came from an unexpected source. One evening, Margaret Hartley was examining a piece of salvaged equipment that had been pulled from a sunken trawler. The ship had struck a mine off the coast of Norfolk. Among the wreckage recovered by divers was a damaged hydrophone array. But this wasn't British equipment. It was German. The U-boat that had laid the mine had apparently been using its own listening device to detect approaching vessels before diving. Hartley carefully disassembled the German hydrophone. The design was ingenious. Instead of a single microphone, it used four, arranged in a square pattern on a rigid frame about 3 feet across. The microphones were connected to a switching mechanism that allowed the operator to compare sounds from different pairs. By noting which pair received a sound first and by how much, the operator could determine the bearing to the source. It was directional, compact, and mobile, exactly what they needed. But there was a problem. The German device was designed to be used from a submarine, in the relative quiet beneath the surface. When Hartley tested it from a surface vessel, the noise from the ship's own engines and propellers overwhelmed everything else. The hydrophones couldn't hear past the racket of the very ship carrying them. They needed to isolate the hydrophones from the ship's noise. Thornton, the submariner, suggested towing the array behind the vessel on a long cable. This would put distance between the hydrophones and the ship's propellers. But how long a cable? Too short, and the ship's noise would still interfere. Too long, and the array would be unmanageable, especially at the slow speeds needed for listening. They experimented. 100 feet, 200. At 300 feet behind a patrol trawler moving at 4 knots, the ship's propeller noise faded to a manageable background rumble. The hydrophones could finally hear what was happening in the water ahead. Christmas 1917 came and went. The team barely noticed. They worked through the holiday, driven by reports of fresh sinkings. On Boxing Day, a U-boat torpedoed a collier off the Isle of Wight. The next day, 2 fishing boats vanished off Cornwall. The pressure was immense. By early January, they had built their first prototype. The array consisted of 4 hydrophones mounted on a cross-shaped frame, weighted to hang vertically in the water. The frame was attached to a 300-foot cable that could be deployed from the stern of a patrol vessel. The hydrophones fed their signals through wires in the cable to a control box on the ship's bridge. An operator could switch between different pairs of hydrophones, comparing the sounds they received. With practice, the operator could determine the bearing to a sound source with reasonable accuracy. But reasonable wasn't good enough. They needed precision. Bennett worked on the mathematics of sound localization. By measuring not just which hydrophone heard a sound first, but the exact time difference between arrivals, they could calculate bearing more accurately. This required better electronics. Hartley designed amplifiers that could boost the faint hydrophone signals without adding too much noise. She scavenged parts from radio equipment, telephone exchanges, even a gramophone. The workshop became a maze of wires, batteries, and jury-rigged circuits. By late January, they were ready for sea trials. The Admiralty assigned them HMS Tamarisk, a patrol trawler that had been hunting U-boats in the Channel with little success. The crew was skeptical. They had seen plenty of new inventions that promised to detect submarines. None had worked. Why would this be different? The first trial took place on a gray morning in early February 1918. Tamarisk steamed out of Portsmouth harbor, the new hydrophone array deployed behind her. The sea was choppy, wind from the southwest. Not ideal conditions, but Ryan wanted to test the equipment in realistic circumstances. They spent the morning listening. The operator, a young sailor named Petty Officer David Mills, sat at the control box with headphones clamped over his ears. He switched between hydrophone pairs, getting a feel for the system. He could hear waves, distant ships, the creak and groan of the trawler's hull. Then, around midday, something different. A rhythmic thrumming, faint but distinct. Mills adjusted the controls, comparing signals. The sound was coming from the southeast, about 30 degrees off the starboard bow. He reported to the bridge. The captain altered course. Tamarisk turned toward the contact, her crew at action stations. The thrumming grew louder. Mills refined his bearing estimate, 25 degrees, 20. The captain ordered a reduction in speed. At 3 knots, barely making way, Tamarisk crept forward. Then they saw it, not a U-boat. A British submarine, HMS L-12, which had been conducting exercises in the area. The submarine was running submerged, unaware of Tamarisk's approach. The trawler's new hydrophones had detected her from over 2 miles away and tracked her to within a few hundred yards. The test was a success. The system worked. But could it distinguish a submarine from other vessels? Could it work in the acoustic chaos of coastal waters? They needed more trials. Over the following weeks, Tamarisk conducted dozens of exercises with friendly submarines. The crew learned the acoustic signature of a submarine, the particular frequency and rhythm of its propellers, the way the sound changed as it maneuvered. Mills became expert at interpreting what he heard. He could tell if a submarine was approaching or moving away, turning or running straight, speeding up or slowing down. The hydrophone array gave him a picture of the underwater world that had been invisible before. By March, the Admiralty was convinced. They ordered production of the new hydrophone systems. Dozens of patrol vessels would be equipped. But there was a problem. The devices required skilled operators. It wasn't enough to hear a submarine. The operator had to interpret complex, often ambiguous sounds, distinguish genuine contacts from false alarms, maintain concentration for hours at a time. The Navy established a training school in Portsmouth. Mills, now promoted to Chief Petty Officer, became the lead instructor. He taught new operators how to listen, how to recognize the signature of different types of vessels, how to filter out background noise, how to stay alert during long, tedious patrols when nothing happened for hours. Then suddenly a contact would appear, and seconds would matter. The first operational deployment came in late March. 6 patrol trawlers equipped with the new hydrophones were assigned to protect the approaches to Liverpool. The port was vital. Convoys from America arrived there weekly, carrying food, fuel, and munitions. U-boats had been sinking ships within sight of the harbor. On March 28th, HMS Daffodil, one of the equipped trawlers, was patrolling off the Mersey estuary. The hydrophone operator detected a contact at dawn. Bearing northeast, range estimated at 3 miles. The captain altered course to investigate. The contact moved, heading south toward the shipping lanes. Daffodil followed, maintaining acoustic contact. The submarine was unaware of pursuit. At 7:15 a.m., the U-boat attacked a merchant ship, the freighter SS Harlington, bound for Liverpool with a cargo of timber. The torpedo struck amidships. Harlington began to sink, but Daffodil was already closing in. The trawler's captain had marked the U-boat's position from the torpedo track. As the submarine began to move away from the sinking ship, Daffodil raced to the spot and dropped a pattern of depth charges. The explosion sent columns of water skyward. Moments later, oil and debris surfaced. The U-boat, later identified as UB-51, had been destroyed. It was the first kill using the new hydrophone technology. Word of the success spread quickly through the fleet. More vessels requested the equipment. By April, over 20 patrol boats and destroyers were equipped. The Admiralty established a production line in Portsmouth, manufacturing hydrophone arrays as fast as materials could be sourced. Hartley's team worked on improvements. They developed better amplifiers, more sensitive microphones, more robust cables that could withstand the harsh marine environment. Bennett refined the mathematical techniques for calculating bearing and range. The operators became more skilled. They learned to work as a team with the ship's captain and crew. When a contact was detected, the hydrophone operator would call out bearings continuously. The captain would maneuver the ship to close the range. The crew would prepare depth charges. It became a deadly dance, the surface vessel stalking its unseen prey. The U-boats began to notice. Submarines that had operated with near impunity in coastal waters now found themselves hunted. Several U-boat commanders reported being attacked by British patrol vessels that seemed to know exactly where they were, even in murky water with poor visibility. The German Navy was baffled. How were the British locating submarines so effectively? In May 1918, HMS Mignonette, a destroyer equipped with the advanced hydrophones, engaged a U-boat off the coast of Scotland. The submarine, UC-78, had been laying mines in the Firth of Forth. Mignonette detected the submarine acoustically and tracked it for over an hour. The U-boat commander, sensing danger, attempted to escape by running along the seabed in shallow water, hoping the acoustic clutter would hide him. But Mignonette's operator, a veteran of dozens of patrols, kept contact. He could distinguish the submarine's propeller signature from the background noise. The destroyer attacked, dropping depth charges in a precise pattern. UC-78 was damaged, forced to surface. The crew abandoned ship before it sank. Interrogation of the captured German sailors revealed their shock at being tracked so effectively. They had believed themselves undetectable in shallow water. By summer 1918, the hydrophone-equipped patrol vessels were having a significant impact. U-boat losses in home waters increased dramatically. In June alone, British forces sank 7 U-boats in coastal areas, 5 of them detected first by hydrophones. The German Naval Command was forced to reconsider their tactics. Operating in shallow, British coastal waters had become too dangerous. U-boats were withdrawn to deeper Atlantic waters where the British hydrophones were less effective. But even there, the technology was evolving. Ryan's team developed larger arrays that could be deployed from destroyers escorting Atlantic convoys. These systems had greater range and sensitivity. They couldn't match the precision of the coastal systems, but they gave convoy escorts a fighting chance to detect approaching U-boats before they reached attack position. The impact on the war was profound. Merchant ship losses in British home waters dropped by over 60% between March and August 1918. Convoys that had been suffering regular attacks now reached port intact. The food situation in Britain stabilized. Rationing continued, but the threat of starvation receded. The war economy, which had been on the brink of collapse, recovered. By September, with American forces arriving in strength and the German army in retreat on the Western Front, the U-boat campaign was effectively over. The submarines that had come so close to winning the war for Germany were now hunted relentlessly. Many never returned from patrol. The final tally was remarkable. Between March and November 1918, British forces using hydrophone detection systems located and destroyed 43 U-boats in home waters and coastal approaches. Dozens more were damaged or forced to abandon their patrols. The technology that Ryan's team had developed in that drafty Portsmouth workshop, working with salvaged equipment and improvised materials, had broken the U-boat stranglehold on Britain. The armistice came in November 1918. The war was over, but the work of the acoustic warfare pioneers continued. The hydrophone technology was refined and improved. It became standard equipment on Royal Navy vessels between the wars. During World War II, descendants of those 1918 hydrophones, now called ASDIC and later sonar, would once again prove crucial in the Battle of the Atlantic. The principles established by Ryan, Bennett, Hartley, and their team, the use of directional arrays, the training of skilled operators, the integration of acoustic detection with tactical maneuvers, became foundational to anti-submarine warfare. Today, every navy in the world uses sophisticated sonar systems descended from those first improvised hydrophone arrays. The technology has advanced beyond recognition, using computers and digital signal processing that the 1918 pioneers could never have imagined. But the basic concept remains the same: listening for the enemy beneath the waves. The story of Britain's hydrophone development in 1917 and 1918 is more than a tale of technical innovation. It's a story of desperation driving creativity, of civilian experts and military personnel working together under immense pressure, of incremental improvements and sudden breakthroughs. It's a reminder that wars are won not just by soldiers on the front lines, but by engineers and scientists working in workshops and laboratories, often far from the fighting, creating the tools that make victory possible. The men and women who gathered in Portsmouth that cold December had no guarantee of success. They were working with incomplete knowledge, limited resources, and a ticking clock. The fate of their nation depended on their ability to solve a problem that had stumped the best minds in the Admiralty. They succeeded because they refused to accept failure, because they learned from every test, every trial, every mistake, because they combined theoretical knowledge with practical experimentation, and because they understood that the lives of thousands of sailors and merchant seamen depended on their work. By the end of 1918, the shallow coastal waters around Britain, which had been a killing ground for merchant shipping, had become a graveyard for U-boats. The hunters had become the hunted. And Britain, the island nation that depended on the sea for survival, had secured its lifeline. The acoustic warfare pioneers of Portsmouth had changed the course of the war and the future of naval combat forever.